Now we'll learn about an application of matrices in biology. And really this starts here with this very simple situation of bacteria dividing and the population growing. Okay, so you've likely seen something like this at one point in your math career. We're just describing the number of bacteria at any given time. Okay, so we're trying to track this number here. And see how it changes over time. So we start at 200, right here. And every hour these double. So at the next hour, where t equals 1, we would have 400. And the next hour is 800. And the next hour, 1600, and so on. We can write that in general as n sub t, so the number of bacteria at time t is just twice the number of bacteria at the previous hour, like that. But look here, this n sub 3, it's 1600, sure, but it's also 2 times what I had in the previous time step, 800. Oh, but this here, this is 2 times what I had in the previous time step. And the same here, this is 2 times what I had in the previous time step. Okay, so you see how that this recursive model comes about. Oh, but now I have an expression for n2 in terms of n1, so I could sub that into here. And I have 2 times 2 times n1. Oh, and this here, this is also 2 times 2 times n0, like that. Now I could sub in that n sub 1 expression here. And I have that. But now look, there's a pattern forming. Here I've got 1 at the first hour. Here the exponent is 1. Here the exponent is 2. Here the exponent's 3. Like this. And so we see, in general, that we can write the size of the population at time t as just the tth power of 2 times the original population size. Okay, and so this gives us an idea of how that population is growing. But it's not a very realistic model of growth because it's exponential, so it just takes off and it just gets bigger and bigger and bigger without limit, which is a little unfortunate. That's not actually how populations grow. So we could start thinking about refining this model to look at different features of a natural population that we might want to consider in our mathematics. Here's one example of such a model. Okay, so I'm imagining a forest here. There's seeds in the forest. These seeds can germinate and grow and turn into saplings, and these saplings can mature a little further to be juveniles, and these juveniles eventually mature and become adults. Okay. There could be other stages, there could be other features in the forest that we could consider, but here we just focus on these. Okay, starting with seeds, you can imagine each seed has a 20% chance of turning into a sapling. And the other 80%, maybe they failed to germinate, maybe they were eaten by squirrels or something, and with that 80% chance, those seeds die. Okay, and once we're at the sapling stage, there's a 50% chance that that sapling will move on to become a juvenile, and another 50% that the sapling's eaten by a deer or succumbs to disease or something and then dies. Okay, and once we're at the juvenile stage, each juvenile has an 80% chance of becoming an adult. Okay, and there's something missing here, a 0.2% chance of that juvenile dying, again, from disease or what have you. And once we're at the adult stage, those adults have a 20% chance of dying or an 80% chance of sticking around into the next year. Okay. There's two other features of this model. That once we're at the juvenile stage, you notice that each juvenile is expected to produce 50 seeds. So then we have this kind of interaction between these two boxes. Juveniles produce 50 seeds, and those go back here and start cycling through those life stages. Similarly, adults produce 100 seeds each year. So each individual adult produces 100 seeds, and these go back to the start of this kind of life cycle and makes its way through the different stage classes. Okay, so what we want to do, of course, is use some mathematics and describe this mathematically. And one way we can do that is by imagining we have a vector of numbers here. Each corresponds to the number of seeds, or saplings, or juveniles, or adults. Okay, so we have absolute numbers for each of these, and we can see how the population changes over time. Now, the way we describe that change is by writing down all these transition probabilities and offspring numbers in a matrix. Okay. So this first row, these are, when I multiply these together, that's going to give me the number of seeds in the next generation. So if I multiply this first row with this vector here, I'm going to get this first entry. So that'll be the number of seeds in the next year. So we'll look how are seeds produced for the next year. You notice that seeds don't stick around, that I have no probability of a seed surviving a year to go on to germinate and turn into a sapling. It just simply either becomes a sapling or it dies in that current year. Okay, so those aren't produced. Saplings don't produce seeds, but juveniles do, and adults do. So when I have a number of juveniles here, and I multiply these two together, that's going to be 50 times that number, and that will give me some contribution to the number of seeds in the next year. Okay, so now I have to look at the number of saplings that are produced. Well, those all come from seeds with a 20% chance. Saplings don't stick around until the next year. Juveniles aren't turned into saplings. Adults aren't turned into saplings. Okay. Now I have to look at the number of juveniles that are produced. Well, the seeds don't become juveniles right away. The saplings become juveniles with 50% chance. Okay. Juveniles don't stick around. They either become adults or die, and adults don't become juveniles. Okay. And now we look at the number of adults. Well, seeds don't become adults. Saplings don't become adults. Juveniles become adults with an 80% chance, and adults stick around into the next population with an 80% chance. Okay. So this is how we would describe cycling through these life stages using these transition probabilities and these offspring numbers. I group them all together in this type of matrix. This is called a Leslie matrix. Leslie matrix. And we can set up this kind of equation, perhaps more abstractly, if I called this matrix L, for example, for Leslie, and here I might call this the number of each of these. It's a vector, the numbers of seeds, saplings, juveniles, and adults. So I'll just write it as N sub t, kind of similar to that bacteria population. When I apply this matrix to this vector of quantities, what I get over here is the vector of quantities in the next hour. That's how this changes. So I could write it perhaps in some shorthand as the vector of quantities in the next hour is equal to the Leslie matrix times the vector of quantities in this current hour. Okay, you should notice this is very, very similar to the bacteria population we just looked at. Okay, we're going to actually see how this works. I'm not going to do those calculations by hand because that's going to be a lot of matrix multiplication. So we can just go to any online calculator. Here I'm just pulling up Symbol Lab. And I can see how such a matrix would work, how the population would change over time. So, pardon me. So I have just the matrix. I'll just enter in here very quickly. 0.2, 0, 0, 0, 0.5. Okay. Remember, as you're seeing these appear, what each one of them means. Okay. So this is that transition matrix. And then I can start with a vector that describes the current makeup of the forest. So I could imagine that I'm only starting with one seed, and I could look at what happens as time goes on. Just multiply these together. Sure enough, I have, well, 0.2 saplings. Really what this means is that I have 20% chance of that seed becoming a sapling. We could up the numbers. We could put maybe 100 seeds. And once we do that, then you see I expect to have 20 saplings for the next day, or the next year. Okay, and I could do that again. So I could change this to be 20. Oh, sorry, I wanted it down here. 20 here. And I could look at what happens as I do this. Sorry about these distracting ads, but I want to show you how we could use online calculators to do this type of calculation. So here we are. So if I had 20 saplings one year, the next year, considering I have a 50% chance of going from sapling to juvenile, I should have 10. Great. And so I can now look at what happens to those 10 juveniles. Oops. These are saplings. These are juveniles. Sure enough, 10 juveniles results in 8 adults, but now also 500 seeds. So that's how it transitions like this. Okay, what we could do is we could imagine that we're really applying this matrix again and again and again to the population size. So if I started at, let's do just 100 seeds, I can apply a power to this matrix. You can imagine it's just repeated matrix multiplication. And I could look at what happens to the population in 5 years, for example. And here we go. It shows the makeup of the forest. I would have 640 seeds hanging around, 160 saplings, 50 juveniles, and about 5 adults. Okay, and I could do this again. I could increase it. And here we go. The numbers are a little odd, but this is what it would look like in 10 years. And I could keep on doing this and see how that population will evolve over, or the population numbers, I should say, should change over time. Okay. So that's what that's looking at here. You could ask yourself, well, if we had different beginning composition of the forest in terms of seeds and juveniles and all that, what would it look like over time? Okay. So I invite you to try it out. There's an example there, and we could do this next time we see each other. But there's one thing I want to talk about, which is kind of a vital topic in linear algebra. It's this notion of finding a vector and a value that doesn't change when I multiply it by a given matrix. Okay, so I had my Leslie matrix multiplied by this vector of quantities, And it's growing all the time, right? Because we're producing more and more seeds, so the population's growing. But I wonder if there is a vector I could find so that when I apply the Leslie matrix to it, the ratio of the entries stays the same, okay? So it's like everything's in proportion to what it was before, and that constant of proportionality is this lambda here. Okay, so it's like it's growing, but it's growing not that there's like more and more and more and more seeds. It's kind of growing proportionally, so the ratios stay fixed. So if we can find such a thing, this vector here is called an eigenvector, and this value here is called an eigenvalue. So it's this vector that doesn't change under matrix multiplication. It just becomes scaled. It becomes longer and longer. So we want to focus on this over this next week and keep on returning to it because it's such a central topic. But let's look at our particular example. And I'm just pulling up just another random matrix calculator on the internet just so we can get some experience in calling on them when we're doing our work. So I'll just put it in, pretty easy to use here. This is just a eigenvector and eigenvalue calculator. And that's what I'm going to get it to do right now when I click find. It's going to find these things called eigenvectors and eigenvalues, okay? And keep in mind they're this v and this lambda that satisfy this equation, okay? So here we are. Here's my original matrix. And then it's a 4x4 matrix, and we'll see what that means in terms of the number of eigenvalues. It means, in fact, you do get 4 eigenvalues. Okay, 2 of them here are complex numbers. So this course doesn't really focus on complex numbers, so we'll put those aside. And you could imagine, if you want to justify why we're putting them aside, you don't see, complex forests so much. So they're not particularly relevant to the context we're working in right now. And as we'll see, that lambda is the growth rate of that forest or that population described by the Leslie matrix. So I want to not consider the negative eigenvalue, because that would mean that the forest is shrinking and eventually die off. And so then I have this positive eigenvalue here, and this is the one case that corresponds to the forest growing, okay? And as it grows, what happens is it kind of maintains this composition in the forest. So as time goes on, for every 1 adult, there's going to be roughly 85 seeds, 7 saplings, and close to 2 juvenile trees. So that's going to be roughly the composition of the forest as time goes on. So let's see how that looks here with our example. So here I've got the forest calculated up to the 10th generation, starting at 100. And if I were to put some of these values in and look at their ratio, I should get approximately this. Okay, so approximately 85 seeds per 1 adult. Okay, and let's try it. I've got 949 adults roughly, and if I multiply it by what the eigenvalue, the first entry of the eigenvector is, which is about 85, and I'll just put it in roughly 85. What I get is pretty close to this value here. Okay, so perhaps if I increase the number of generations I look at, I would get closer and closer to this value if I use more and more precise numbers. But what this is saying, this eigenvalue and eigenvector, it's showing the long-term proportion of all the life stages present in the forest. Okay, so that's a pretty interesting observation we could make, and we're going to follow up on that next day.